Hello everybody, welcome to the next day of our tutorial. Today we are going to solve the third problem set from the Eigensolvers Quantum School. Its theme was sharing quantum states. Let's begin. Let me read the first problem. In the section about superdense coding, we mentioned that Bob can do a Bell state measurement on the entangled pair of qubits to identify the bit string that Alice encoded. However, if Bob has access to a quantum computer that can only do measurements in the computational basis, he still can decode the bits Alice was trying to send. Draw a circuit that Bob must use to do this. So basically, usually it is said that Bob measures this pair of qubits in the Bell state basis, right? So it's a basis that contains Bell states that we are talking about, for example, in the last programming section of tutorial 2. So we can only, it can happen that we can only measure in computational basis, right? Which is a standard basis for measurements. Then we can still do that. We can still do measurements in Bell state basis. And this problem is intended to show you how to do that and that it is in fact possible. So let's try with drawing the circuit that goes the other way around. That puts these computational basis elements into entangled Bell states. I mean, this circuit, right, that we know from previous lectures, transforms 0, 0 to phi plus, right? 0, 1 to phi minus, 1, 0 to psi plus, and 1, 1 to psi minus, right? So this is the reverse transformation that we want to get. So we want this one to reverse. So let's try to actually change the order of these gates, okay? Because if we take C naught, then in these cases where it actually bit flipped the second qubit, it will bit flip it again, right? Because the control bit is the same, the control qubit actually. And then we can apply Hadamard gate, because Hadamard is its own inverse, right? So it should work. At least our intuition is so that it should work. And we can just verify that it actually works. So let's take phi plus, for example, okay? So it's 1 over square root of 2, 0, 0 plus 1, 1, right? And let's check what this transformation does to this state. So C naught bit flips the second qubit only in this part of the superposition, right? It doesn't change 0, 0 at all. So C naught transforms it to 0, 0 plus it's 0, 1, right? Because first qubit is on the right and second one is on the left. We can also write it as a tensor product. It will be nicer to look at it. So it's 0 times plus, right? Because here we have 0 plus 1. And actually I can then erase this 1 over square root of 2 because it's part of plus. It's a normalization factor. And then when we apply Hadamard times identity, right? Because we do nothing to the second qubit, then we get 0 times 0, right? Because Hadamard transforms plus to 0. That's of course 0, 0, right? We can also check that it holds for other cases. For example, for 5 minus, it's very easy now, because we can just instead of this plus consider minus here. Then it will be still minus here, right? But here we will get just minus, right? So it will be in this second case, so maybe here in the case I will erase this and I will write that this is the case when we talk about phi plus, and this is the case when we start with phi minus, right? Phi minus, and then we get minus here instead of plus, okay? And it is 0 and 1, right? 1, because minus goes to 1, and it's 0, 1, as it should be, right? We can also quickly verify that it also holds for psi plus and psi minus. So 0, 1, or actually, yeah, 0, 1, plus minus. We will deal with two cases at once, okay? C naught transforms it to 1, 1, yes, because the first qubit is 1 here, so it bit flips the second one. And here it is 0, so it does nothing to the second one. So it stays, it remains 1, 0. Nothing's changed here. And then we apply Hadamard times identity, right? So we get, of course, we can also write it first as a tensor product to better see what happens. This is just 1, yes, and this is 1 plus 0 or 1 minus 0, okay, so it's plus in the first case and minus in the second one, and that, okay, and of course, as before, I erase this 1 over square root of 2, and then it goes to, if it is psi plus, we get 1, 0, and if it's psi minus, we get 1, 1. What agrees with what we wanted to get. So that's the circuit, that's the answer. Of course, we have to get some measurements on the end, right? Because that's the part of the superdense coding protocol. So we can go to the second problem. Now a problem that touches on BB84 cryptographic protocol. So Alice is sending a total of 10 qubits to Bob, and for each of these qubits, she chooses a bit 0 or 1 with equal probability. Then chooses one of the bases, right? A computational one, which is called R in this context, or the one containing plus and minus states, which is called D here, with equal probability. And Bob randomly chooses a measurement basis, one of the same ones, R or D, also with equal probability. So the first question is, what is the expected number of bits that Alice and Bob will add to their keys? And assume there is no eavesdropping, okay? So, and what does mean that we also assume in this context that there is no noise, the channel is an ideal one. So let's remind that Alice and Bob add to their list, to their key, a bit if it turned out that they chose the same basis, right? So actually, it doesn't matter. So actually, what we should do is just list all the possible scenarios of those basis choices, right? So Alice can choose R or D, yes? And Bob can also choose R or D. So possibilities are that both choose R, that Alice chooses R and Bob D, Alice D and Bob R, or both choose D. Okay, we have 4 equally probable possibilities. Yes, all of them are probable with 1 over 4th, right? And they add the outcome bit to the key only if they happen to be in one of these possibilities. Yes. So the probability that that they add a measured bit to the key, right? Bit added to the key is 2/4, which is 1/2, right? Which is a half. Because these are two possibilities out of 4, all of them are equally probable, so we can just write it as this this formula. And what is the expected number? Well, if number of those bits, right? So if they measured it 10 times, then the expected number of bits in the key is just 1/2 times 10, which is 5, right? Okay, now Eve is eavesdropping in the quantum channel and measures all of the qubits in the R basis, so the computational basis, before they reach Bob. Now, what is the expected number of bits that Alice and Bob add to their keys? What is the probability that the first bit in Alice's key is the same as the first bit in Bob's key? So let's observe that Alice and Bob add a bit to their key if and only if they chose the same basis, right? The only condition is the choice of a common basis. So it doesn't matter whether there was some eavesdropper in between of them, right? The only thing that matters is the agreement upon common basis. So actually the expected number of bits in the private key that they construct doesn't change. The answer is still 5. So as well as probability of adding bit to the key doesn't change as well. However, the fact of Eve eavesdropping influences the probability of having the same bits in both Alice's and Bob's keys on specific positions, for example, on the first position, on the very beginning, right? So how can we find the probability of having the same bit? Well, as we said before, we have these 4 possibilities of choosing bases, right? Also, I will write that if measures in R, right, which is computational basis. And she always measures it in this basis. So we have 1/2 probability that a bit won't be chosen for the key, right? So not added to the key, right? And we have also, or maybe I will write it as RD or DR. These are these 2 possibilities. And the other possibility, two other possibilities are RR or DD, right? And they both have 1/4 chances to appear. And that means that we can just consider these 2 scenarios and then compute the whole probability of success. So here, if we have this basis, then Eve measures the qubit in the same basis as Bob. So even though she collapses the state, it still gives the same. It should still give the same outcome as in Alice's measurement. I mean, Bob will measure the same as Alice, because even though Eve collapses the state, the qubit, it should collapse to the same what Alice measures, right? Because these 2 qubits are in entanglement, so they should collapse to the same thing. And Bob will just measure the already collapsed qubit, but it doesn't change anything, right? So with probability 1, we will get the same bit, the same bit. And here, Eve will collapse this qubit to either 0 or 1, while Bob will measure this 0 or 1 in this basis +1, right? In this basis. So for both of them, for both 0 and 1, it will, with equal probability, 1/2 go to plus or minus, right? He will measure with equal probability one of them, regardless of to what Eve collapsed the state, whether it is 0 or 1, it still gives equal chances to get plus or minus in Bob's measurement, right? So it's 1/2 that we get the same bit as Alice, and 1/2 that we get something else, right? Not the same bit, a different bit actually. Yeah. So we now can compute this probability of having the same bit, right? The same bit. Actually, the question is, what is the probability that the first bit is the same as the first bit in Bob's key? So we need to ignore this part, right? Because it doesn't add anything to the key. So we need to compute this conditional probability, which means that we take this 1/4 times 1 plus 1/4 times 1/2, right? Because this is what we want to get. And we divide it by probability of getting a bit to the key. So it's 1/4 plus 1/4. Okay, I'm gonna erase this to make more space. And this is 1/2. Here 1/4 plus 1/8. And we get 2/4 plus 2/8, which is, maybe I will continue here, 1/2 plus 1/4, which gives 3/4. And that's the probability that we were looking for. So the probability that Alice and Bob get the same bit in the first place is 3/4. Okay, and now Eve measures those bits in a different basis, which is a basis y. It changes a bit our tree, because now, of course, we have still 1/2 probability of not adding the measured bit to the key. But here, okay, here it is all still the same. But now, while here we had a certain correct measurement, because with probability 1 we knew that this will be the same bit measured in both Alice's and Bob's circuits. Now we don't know that, because these states will collapse this qubit to Eve will collapse to this qubit to one of these states, right? And those measured in both D and R bases will collapse to 0 and 1 with equal probability, or plus or minus with equal probability. So we will have 1/2, and here will be the same, right? The same bit, and here different bit, and here as well the same and different, right? And now we can compute the probability. of the same bit, which is going to be, of course, here we have still 2/4 as before, because these are the only branches in which we add a bit to the key. But now we have here 1/4 times 1 second and 1/4 time 1 second, right? Because here we have also 2 halves. This means that we have 1/8 plus 1/8 over 1 second, which means we have 1/4 over 1 second, which means 2/4, 1/2. So this time the probability is 1/2. And that was the last question from the theoretical part. Now for the Qiskit exercise part. Let's import necessary libraries, and we can start with problem 1. So this is the transformation from the computational basis for 2 qubits to Bell states basis, right? Basis consisting of those entangled states. And we discussed it in the theoretical part of this tutorial, so I will just implement the circuit that I presented earlier. So this is, of course, Hadamard 20 and CX01. And this maps these qubits in the way 0, 0 goes to phi plus, 0, 1 to phi minus, and so on. And this part of the code will allow us to check whether this answer is correct. Yes, it's correct. We can go on. Problem 2, quantum teleportation. And here we're going to implement the teleportation protocol. A is Alice's qubit that forms half of the entangled pair, and B is Bob's part of this entanglement. And C is the actual qubit that we are going to teleport. I mean, we are going to collapse this qubit and teleport its quantum information to qubit B, right? In such a way that Bob receives this information stored in that qubit. And M1 and M2 are classical registers for our measurement. Okay, so let's start with entangling both qubits, one from Alice and one from Bob. We can do that with the same circuit that we used above in problem 1. So it's QCH0. Now it is A, because we called our quantum register qubits as A, B, and C, right? QCCX A, B. So now these 2 qubits will be entangled. And what we want to do next is to entangle Alice's qubit C with this pair, right? So QCCX CA. So Alice does this entanglement between her 2 qubits. Also QCH C. And now Alice can measure her both qubits, collapsing this state, right? QC measure A M1 and QC measure C M2. And that is the moment where Bob starts doing something. So if you remember from the lecture, if these outcomes are 0, 0, he does nothing. If it's 0, 1, he applies X to his qubit. And if it's 1, 0, he applies Z. And if it's 1, 1, he applies both of these gates. So he applies X and Z. We can do that with conditionals, of course, like if statements in Python. But I think the more elegant form is to do CX and CZ gates methods. I mean, we can just do, we can apply CX with target at A, okay? Control at A and target at B, right? So if A is 0, it does nothing, and if it is 1, it bit flips B, so it applies X, right? That's how CX is defined, and the same for CZ applied to C and B, right? Because notice that when we measure these qubits in the computational basis, these qubits collapse to the state that they were measured in. So they are in 0 or 1 states, right? And that's why it should work. And that's actually all. We can also display our circuit. Okay. And that should work. Yeah, so that's it. And let's check, does it work? Yes, your circuit is correct. You can move forward. Yeah, there's nothing forward, so that's all for today. I hope you learned something new from the third day of the school, and see you in the next material, in the next tutorial. As always, feel free to keep in touch through Discord server. Bye.